Okay, welcome to the forecasting lab in Python. This lab assumes that you have seen my advanced forecasting lectures to understand the theory. Now, obviously, you can finish the lab without understanding the theory, but it will make a whole lot more sense if you do. These lectures are part of my Global Supply Chain Management course. If you have not done the course with me, or you missed the lecture somehow, they're linked here. So when you open this lab file, you can click the links and go watch them. Now, the file, this interactive Python notebook, IPYNB file, is provided to you on Canvas, and you need to upload it onto colab.research.google.com. The way you do it is first you sign into your Gmail and then you go to Google Drive. Okay. When you're on Google Drive, it should have a folder called Colab Notebooks. Okay. And you can actually access that folder by connecting your Google Drive to this notebook by using this button. Go to Files and use this button. In any case, inside Colab Notebooks, any notebooks that you have, you can double click them and open them. So if you upload this file to your Google Drive inside the COLAB, let me write it down, up maybe here. Move it up. Okay, this this .ipynb file should be placed in the Colab Notebooks folder on your Google Drive. Double clicking this file from that folder will open up this Google Colab workspace. Okay, and so that's how you get started. You also there's a data file associated with this lab called airpassengers.csv. Should be placed in a data folder inside Colab Notebooks folder on your Google Drive. So when you go to Colab Notebooks, you can do a new folder, create a new folder in Google Drive called Data, and then put the data file inside that. The data file could just be in Colab Notebooks as well, doesn't matter, but it's just easy to keep things separate, have data, the CSV file inside the data folder. Once you put these two files there, then you can double click on this file in your Google Drive and open this workspace and get started. If you have any issues, you can just go to this link and go to Upload Notebook, and then upload this starter notebook from your computer onto this Colab Notebooks. And then for data, you can drag and put the file in this space right here, drag the CSV file, and you'll be able to access it. But this space gets cleaned out when you close this workspace, because it's running on a virtual machine and the virtual machine gets closed down. And so it's better to just put the data file on Google Drive and then open it in this lab through Google Drive. Okay, so now that you're set up, we're going to start by applying several different forecasting methods to this data file. And we're going to start with two rather simple methods called Holt-Winters model with additive seasonality and multiplicative seasonality. Okay, and these models, the reason we're starting with these models is that these models are often used in Excel because you can kind of do these calculations in Excel. And so I'm going to show you how to apply these models in Excel, where you can see each step-by-step calculation. So then when we move to Python, you'll be able to see, okay, how is Python doing the same thing or achieving the same thing? I think it's helpful to compare Excel with Python for these models, just so you get an understanding of how to do things in Python, because a lot of your Excel work can be ported to Python, and then you'll also see the advantage of doing it in Python. So I've placed the formulas here. The formulas are covered in these lecture slides and explained here. Essentially, you have state called level L, trend B, and seasonality S. And based on this state, you forecast for the next time period. Then when you observe the data for the next time period, you can update your state. And so these are called state space models or ETS models, and they're covered in these lectures. Okay, so let's look at the data in Excel, and let's see how you would do this Holt-Winters model for forecasting, both of these in Excel, and then we'll jump right back and do the same thing in Python. Okay, so this is the first column. Okay, let's actually call it month year, because it's year and month. So this column, month year, and the num passengers column is what is the data given to you. So you're given, for each year, you're given the 12 months. Okay, and you're given how many thousands of passengers chose air travel or flew in an aeroplane to travel in the US in that year and month. Now, our goal is to predict, for the next year, how many passengers we expect to travel using air travel. Because let's say we're an airline with, let's say, 30% market share. Once we figure out how many people will travel next year in each month, we can figure out how many customers to expect, because 30% of that is the volume that's probably going to come to us. Okay. Okay, so how do we build the Holt-Winters model? This is just to show you what the raw data looks like, right? So you have the month year column with the year and month, and then you just have the number of passengers. That's the data we start with. Okay. So the first thing I do is I split up the year and the month. Okay. The reason being that I need to know which month it is for my seasonality calculation. It helps me, and it's easier for me to process it like this in Excel rather than try to extract the month from this combined field. This is just a string, so the function I can use is I can say equals left to give me the left part of the string, then select the cell with the string, and I need 4 characters. So that'll give me the year. Then you can drag it down, and then Excel will say, oh, looks like you have a number stored in a string, and then you can click that, and like if you go here, anyway, so then you can convert it to a number. You can go here and go to format cells and pick number instead of a string, and that becomes a number. Okay. Okay, so that's how you extract the year. And this here is also relatively easy to write, because you want the right, you just want to get the characters from the right, which is 0 and 1. This is the string to process, and you want the 2 rightmost characters, and that gives you the month. Okay, so that's how I extracted this string, which has the year dash the month, into year and month. Okay. And then this is given in the data file. So we have this state called level, trend, and seasonality. So we need columns to keep track of this state. So we create 3 new columns: level, trend, seasonality. They will be empty, and then we will fill them with values that we calculate. And then we add a column called forecast, which will contain our forecast. And then we calculate the error and so on. Now, the important thing to realize is if you look at the whole data, you have 1949 to 1960, about 11 years of data. The first year I've shaded gray. The reason being that to run this algorithm properly, you need to initialize your state. You need to have some initial estimate of level, trend, and seasonality. And you need a year's worth of data to set up your initial estimates, because you need a seasonality parameter for each of the 12 months. And unless you've seen each month at least once, you cannot set up your seasonality estimates. So the first year, we're not going to calculate any error or try to evaluate the performance of the algorithm on the first year of data, because the first year of data is just used to initialize the algorithm and compute initial estimates of level, trend, and seasonality. And then from year 2, we're going to actually look at our forecast compared with the actual, calculate our error, and do all that. So that's the white part of our data, which I've not shaded. And then at the end, I have generated the year and the month for the next year, 1961, 12 months. And this will, the green area here will contain my forecast for next year. Obviously, I don't know the actual values for next year, so I cannot compute the error for next year. Okay, so the year at the end in green is next year, for which we don't know the true values. The first year in the beginning is the data we use to initialize our algorithm state. And so we don't calculate error on the gray part because we're initializing state. We don't calculate error on the green part because we cannot, because we don't have the actual data. It's just a forecast of the future. But in the middle, the white part is where we are forecasting based, we have initialized our algorithm and actually producing forecasts that, we can use. And so we compare those forecasts to actual sales data to get an idea of the error. Okay, so that's the three kind of regions. So in the, let's zoom in. Now, if you look at these formulas, we'll implement these formulas like the way they are starting in the white part. In the gray part, the first we have to initialize the level, the trend, and the seasonality. So let me explain the logic here. So let's say you have 12 values. This is the data we have for the first year. Okay, and the values are up and down like this. Okay, now we want to estimate the level in the first month, or L of 1. Okay, and if we take the average of the 12 months, okay, the average over the 12 months will give us the level in the middle of the year, at the end of month 6, between month 6 and 7. So it'll give us maybe let's say L6, or maybe we can call it L7, something like that, the level here. Now, the level is what the trend acts on, because level at the next time period, t plus 1, is level at the old time period plus the trend. Trend is the change in level. If there's no trend, the level stays the same, right? You stay at the same level. Okay. So if I take the average of the first 12 months, I get an estimate of the level here. I can use that to estimate the level here by subtracting my trend times 6 months. Because between month 1 and month 7, 6 times has trend acted upon L1 to get to L7. Okay, so that's what we do in the beginning. Okay, I take the average of the first 12 values. That gives me the level in the middle of the year, like L7. Then I subtract my trend, which is in F2, times 6. Okay, now what is this M period over 2? M period is 12, because 12 is the after 12 time periods, my seasonality repeats. So my seasonality is over months. So every 12 months, January comes again. So the January seasonal effect comes every 12 months. The February seasonal effect comes every 12 months, right? That's the period after which my seasonality pattern repeats. If you have daily data and you have seasonality over days of the week, like Monday, Tuesday, Wednesday, then M will be 7, because every 7 time periods your seasonality pattern repeats. If you have quarterly data with 4 quarters per year, then M will be 4, because every 4 quarters your quarterly seasonality pattern will repeat. So, how do if you have a cell with a constant like this, 12, I can click here and give it a name. So I've given cell M4 the name M period, which stands for the seasonality period. So I take the average of the first 12 values of the data. That gives me the level in the middle of the year. Then I subtract 12 over 2, which is 6, times the trend, to figure out what my level should be in the beginning. Now, how you initialize is not that important. You could initialize trend to just be the average of the first 12 months. It will not make a big difference. But this is the logic why I'm saying that if you take the average over the 12 months, then you subtract 6 times B from that to get an estimate of the level in month 1. Now, to get this estimate, I need to know what F2 is. What is the trend? So this is all empty in the beginning, right? So how do I get trend in the starting? What's my trend here? Well, I use the same sort of logic. Okay. Let me draw a new figure. Okay, so I have monthly data up to 12. That's my first year. Then 13th month is starting my second year, all the way up to 24. So I use 2 years of data. Okay. I find, let's say my first year of data is something like this. So this is the average value in the first year. And let's say my second year of data is something like this. And I find the average in the second year. Okay, so I have my first year average, and I have my second year average. My second year average is an estimate of my level in the middle of the second year at like month 18. That's like L18. And this is the estimate of my trend at like L7. So between these two estimates, I have 12 months. So the difference between the second year average and the first year average, so average 2 minus average 1, is basically the increase that happened over 12 months, or the trend over 12 months. So this difference in average divided by 12 gives me the monthly change estimate for B. What is my monthly change in the level? Okay, so what I do is I take the average over the second year minus the average over the first year, divide by 12, which is M period, to get my estimate of trend. And then I'm going to update the estimate of trend using this equation for B. My seasonality estimate is going to be how much higher or lower each month's sales is from the annual average. So I take the average of the whole year. That's average D2 to D13. And then I take the actual value for this month and I subtract out the average for the year, because average for the year removes seasonality. It's over 12 months. And so I say, okay, if D2 is smaller than the annual monthly average, that means there's a negative seasonal effect. On average in January, less people travel. So that's my negative seasonal effect for January. And I do that for all 12 values of the first year. So I estimated my first value of level, estimate my first estimate the first value of trend. I use that to estimate the first value for level. Okay, and then I can estimate all the 12 seasonality time periods by looking at each value here and comparing it with the average monthly demand for the first 12 months. Okay. Now there are other initialization methods. Some people will use regression over the first 12 months to get an estimate of the trend. The slope of the regression line will give you an estimate of the trend. The y-intercept of the regression line of these 12 months will give you the estimate of the initial level. So that's also very useful. You just fit a straight line to these 12 points like this. So you do insert a line chart. Okay, then you can add a trend line, display the equation. Okay, and you can see that the y-intercept is 127, so your level estimate will be 127, and the slope, actually because the seasonality you need 2 years of data, so actually I need to do it over 2 years, not 1 year. Because otherwise, sales may dip in the last month, and that might show you, oh, the trend is negative. So you want to do 2 years, and now you'll see, okay, so my y-intercept 121 is the estimate of my level, and 0.97 is the estimate of the trend. So you can just do regression over the first 2 years to estimate your starting level and trend as well. Okay, and you can see the values are very close to what I estimated using my just pure logic, understanding how trend and level components interact. Okay, so you could do that too. There are other initialization methods. If you have few years of data, how you initialize doesn't matter that much, because these update equations will update the values to match the data correctly as you move forward. Okay. Then we enter this equation that the value of trend is given by beta, which is a constant right here. Beta is 0.1. So I'm using these starting values. You can play around with these parameters. These are just called learning parameters. A high value up there between 0 and 1. A value near 1 means you're trying to learn a lot from the last value. A value closer to 0 means you're taking a lot of the past values into consideration. You're not changing too much after each observation, but you say, okay, all like the past 10, 20 values matter, not just the most recent value. So I'm not going to change a lot if I see a change in the most recent value. So these are learning parameters. How fast do you change your forecast based on a change in the value of y? So I'm just using these values to start off with, 0.5, 0.1, and 0.6. Gamma is the learning parameter for seasonality components. Beta is the learning parameter for the trend component, and alpha is the learning parameter for the level component. If you don't know what level, trend, and seasonality components are, again, you can go back to the lectures I've linked in the notebook, Python notebook. If you click those links, you can see the YouTube videos which explain the theory behind all of this. Okay. So I just entered this equation here, and you can see that it's beta times E3 minus E2, which is the change in level, LT minus LT minus 1, right? So that is just 123 minus 120 times beta plus 1 minus beta times the old value of trend. That gives you right here. And this equation will update the trend based on the new value of level 123 that we estimate. You can update the level based on the old value by comparing with the latest value of y, okay, subtracting the seasonality, multiplying that by alpha plus 1 minus alpha times the old level plus trend, because level plus trend, the old values, are like a forecast for the new level. So the new level is supposed to be 121.2 something, okay? So that's this E2 plus F2, that's the expected new value of the trend. And then the actual expected new value of the trend is 118 minus the seasonality. Okay, and then we combine them with alpha weighted by alpha and 1 minus alpha, and that's how we update the level component. And we can't update the seasonality component because to update, let's say, the seasonality for March, the third month, you need to experience another March. So when you come down here, next year's March, then you can update this seasonality factor for March. You can see I've got updated from 5.33 to 6.91. So then you drag these formulas down to fill out the level and the trend. And then once you get here, now you need to update these formulas because in this initialization phase, we were using the seasonality in the same row, but you're actually supposed to use the seasonality from 12 months ago when you update the level, see ST minus M. And so here, what we do is to update the level, we use the seasonality from the last January because, you know, we are going to update the seasonality for this January here, and we haven't done that yet, so we estimate the level first using the last year's January. Same thing for February, use the last year's February. March, use last year's March. Okay. Beta formula stays the same, you can just drag it down. The seasonality formula changes. Now you're going to use gamma times your new estimate of seasonality from the current value, YT minus LT minus BT. LT and BT are for the past time period, T minus 1, BT minus 1, these two. Okay, so from 115 you subtract 127 and then 0.6. And that's your new estimate of the seasonality for January. So you multiply it by gamma and then you weigh the old estimate for the seasonality for January minus 14 with 1 minus gamma, and you can put a weighted average to find the new estimate of seasonality for January. So you know here, for example, there's no formula using the gamma to update the seasonality because you only have one observation per seasonal index. But in year 2 now you have a new observation for the same month and you have the old observation for the same month, and you combine them using this weighted average by gamma. So once you enter these equations, you can go all the way down till here, and you have the actual value, you have the forecasted value right here. So you can see 432, 437 is the forecast, pretty close. 461, 443, pretty close. Okay. And then how do you forecast for the next 12 months? Because you can't estimate level and seasonality for the next 12 months because you don't know Y of t. You need Y of t to update, level and then seasonality. So all you do is you keep this constant, the value of level. So we keep this level, you keep this trend, okay, and you use the last 12 months of seasonality. And then you just use this Y equation. H is how many time periods in future you're looking at. So YT plus 1 would be the level in the past plus 1, H is 1 times the trend in the past plus the most recent seasonal index for that relevant month. Okay. So if you look at this formula, all we do is we take the last level plus trend times 1 plus the most recent seasonality, and that'll be our forecast for January. For February, we take the most the last trend that we estimated plus the last level we estimated, 496, plus the last trend we estimated of 4 times 2, because we're going to need to go 2 months in advance from this month of December 1960. February 1961 is 2 months ahead. So we multiply by 2, which is right here. And then we add the seasonal index for the February, the most recent February for which we have a seasonal index. And that's how we can estimate 12 months out. Then we can just plot. Okay, and here's the plot. The blue line is the actual data. The orange line is our forecast. And you see the orange line goes up 12 months ahead. And you can see it's pretty accurately tracking the signal. And if you calculate the MAPE, it's about 4% error. MAD means you're off by plus minus 11 to 12 on average. So that's your mean absolute deviation of the error. Okay. Now I'm not going to go into so much detail to explain the multiplicative seasonality model because there's only 2 things that change. Before, in the level equation, we were subtracting the seasonal index from the level, But now, see, we're subtracting YT minus ST. Now we're going to divide it, because now the seasonal index is going to become a ratio. 1.1 means 10% more sales than the average. 0.9 means 10% less sales than the average. So, it relative to 1. 1 means the same sales as the annual average, annual monthly average. So we divide by the seasonal index here, and also in updating the seasonal index ST, this equation, we divide YT by LT minus 1 plus BT minus 1, that whole thing. And so this used to be a minus as well. So two of the minuses in our equation becomes division signs, and that's all we do. So instead of, the annual average minus the actual sales minus the annual average, you do the actual sales divided by the annual average to estimate the initial seasonal indices. Then we just update this level equation and the seasonal index equations to have these, not the forecast, this one, to have this division right here instead of the subtraction sign. So it's the exact same thing, except in two of the formulas, the subtraction becomes a division, and then we have a multiplicative seasonality model. We do everything else exactly the same, and we get this graph. Again, very good tracking. A little bit worse than additive seasonality. You can see that's a little bit better. Maybe they're about the same. And if you look at the errors, very close, 3.95% multiplicative seasonality, 4.1% MAPE in additive seasonality. So both methods do really well. About the same for this data set. So this is in Excel. Now the problem with Excel is when you get new data. So let's say you get data for 1961 January. You have to enter the data here, then you have to drag the formulas down. Then you have to update all of these forecast formulas, because now this formula for February can't be based on the level and trend from December 1960. It must be based on this stuff, the level and trend in the most recent month. So you have to update all of these formulas. Maybe now you can forecast another month out or something. So you have to drag and change formulas and do all sorts of manual work each time your data set changes or updates. Okay. The other issue is you built this whole Holt-Winters model into Excel file, but it only works with this data. What if you got quarterly data on your company's sales and you wanted to apply the same model on that quarterly data? You can't, because the formulas are tied to 12 months here, and the positions, right? When I select this seasonality formula here, this cell 5.33 is 12 cells above it. There's a difference here. I'll have to drag it down to make it 4 cells above it if I had quarterly data. So you have to make massive changes to your Excel file to run the model on any other data or to incorporate new data, which is extremely cumbersome. And imagine you had to do this model for, let's say, 100 different SKUs or products your company sells. You build the model once. Now the other SKUs, you may have, some SKUs may have weekday seasonality and you have daily data. You have to focus on a daily level. Some you may want to focus on a quarterly level. Even if they were exactly the same data structure, like monthly data, you would have to replace this data with the second product's data, look at the forecast, copy paste it somewhere else, then replace this data with the third product's data. The formulas would update. Copy paste the forecast somewhere else is just too much manual work. It's just crazy. And so Excel is pretty limited. You can do one-off forecasting for just one series, but you can't handle changes in data, new data. You can't handle applying it to different time periods of seasonality, or you can't handle applying it to many different products or categories. And so Excel has always been very limited for forecasting, but this is how you would do it in Excel. Now, I'm not going to give you the Excel file because all the formulas I've already shown you. You should be at a level, if you're taking the capstone course, where you can build an Excel sheet like this. You can look at these equations, you have the data, you can build this, especially once I've talked through this, I've shown you the formulas, right? You should be able to build this on your own. All this not required for the Python lab. You're not going to have to submit an Excel file. You can do the Python coding and submit that, but you should be able to build this Excel file yourself as well. Now let's go do the same thing, this additive model and the multiplicative seasonality model in Python. Okay, so now we're gonna do this in Python. And as you know, Python, we basically just call different functions in different libraries. In lab 1, you saw these. Actually, we're not going to use C1. You saw us use these library. Pandas is used to store our data in a data frame, and then we can do lots of things on the data. NumPy provides functions like np.mean to calculate averages. Matplotlib gives us the plotting package to plot time series data. And then if you go to here and you mount the Google Drive, it generates this code which attaches your Google Drive so you can open files directly from your Google Drive. So we are gonna run this cell, and it says connect to Google Drive, and you said continue, okay, continue, and now it's connected to your Google Drive, and now I can actually load files from Google Drive. So what I've done for you is I've already provided you these functions, because def defines a function in Python with these inputs. So I've already defined functions which implement these formulas. Okay. And I'm just going to go over these functions to explain the code, but you don't have to do it yourself. You're just going to call this function to run the Holt-Winters algorithm. So you're going to start with this lab. You're going to go over these functions, and you're going to come here, and then you're going to start writing your code to do the forecasting by calling these functions. So this functions, the advantage over Excel is you can pass in any data, this, air passengers data, quarterly data, daily data, to it. It'll run the forecasting. You can specify which column in your data frame actually has the values that you want to forecast, because you could have multiple columns, like a price column or some other column. MP specifies the seasonality period. It's set by default to 12, but it will be set to whatever value you pass in. Assigning a default value means if you're usually going to work with monthly data, then you can skip passing this parameter to this function, and it'll by default go to 12. And then the alpha, beta, gamma, the learning parameters, these are default values. You can overwrite them by other values you pass in. So let's look at Holt-Winters additive function, which is going to implement these equations right here. So the first thing we do is we make a copy of the data, because we don't want to mess with the data the user passed in, because we have to, remember, add these columns to save states and level, trend, seasonality. So we're going to have to, update the data frame to have these new columns to track the state. And so, we don't want to mess with the original data set the user passed in. So we make a copy of the data. Then we just add these 4 columns to this data set: level, trend, seasonality to take state, and the forecast column will actually hold our forecast. np.full is a function from the NumPy package as imported as np, which repeats a value. In this case, it repeats this value, which is not a number. NaN stands for not a number. It's just like a placeholder when you don't know what value will be. And length of the data frame will tell you how many rows there are. So we create a column of the same size, same length, which is full of not a number values initially, and that gets attached to a new column called trend in my data frame. Okay, then I want to sort, because it's very common for time series data sets to be indexed on the date or time column. So I want to make sure that my data goes from the oldest value to the most recent value. If it's not sorted like that, then these equations will not work well, because if you look at these equations, t is the time index, and you go to, if you want to calculate the trend at time t, you want to look at the previous value at t minus 1. But if it's not sorted, the t minus 1 value may not be the value of the previous time period. So we sort the data just to make sure it's in the right order, although usually data would already be sorted, but we don't want to have an error in our calculation. Okay. Then we save, let me actually show you what an index is. So let's actually go and load up our data so we can see, and I can then show you what's going to happen. Okay. So to load up our data, we're going to say data equals pandas PD, PD, and we can use the read CSV function, okay? And then the path, if the file is on our Google Drive, it's going to be content/drive/my drive. Now this is where your Google Drive is. And I saved my data inside Colab Notebooks folder. And I made a data folder inside it. And inside that is this file called airpassengers.csv. Okay. And then you can do data.head to see the first few rows to see what our data looks like. So you can see our data right now looks like this. And this is our date time column. It's currently not date time, because if you look at the D types, the data types of this data, it's an object. So we're going to convert this into a date time. And you can pass in how many rows you want to see for head into a date time column. And this is going to be the index. Okay. So now when we are running these formulas, we want the index to be just 0, 1, 2, 3, kind of like this. This needs to be 0, 1, 2, 3. A lot of times, time series data sets have an index which is set as the date. It's not 0, 1, 2, 3 like that. So 0, 1, 2, 3 are like row numbers, like in Excel, right? This is row 4, row 5, row 6. So we want to work with row numbers, not dates as our index. So we sort the data, we save the name of the old index, then we reset the index to be 0, 1, 2, 3, just like Excel. And now I can say df.location 0 and get the 0th row. Okay, so that's what I do. And then I save that old index, because when I go to forecast the future values, okay, the future values, I need to project this date into the future. I need to know what the last date was, what year, what month, what day, and I need to be able to project that date forward. If that last date was in the index column, I want to be able to project that forward. So I save the old index, then I reset it so I can access it with the .location function with row 0, row 1, and so on. And then I do my initial estimate. So this one is my trend estimate, which is the mean of the first 12 values. No, this is the trend estimate, which is the mean of the second year of data. So MP is the 12 to 24 months, second year of data, minus the mean of the first year of data, divided by 12 to get the monthly change in level, which is my trend. So that's what I assigned to my trend, just like I did in Excel. I took the average for the second year minus the average for the first year divided by 12. So I do the exact same thing in Python. Average for the second year minus average for the first year divided by 12, which is my MP variable. Then I save that in row 0 for my trend. In row 0 for my level, I take the average for the first year, and I subtract 6 times the trend estimate to move it back. Just the thing I explained here, how if you get the average for the whole year, that's like the level at the middle of the year, then you move it back by 6 months to get the, and this is initialization. You remember you could do using regression as well over the first 2 years. So there's many ways to initialize. I'm just initializing using this way. Okay? And then for my seasonality, okay, I go in this loop and I'm going to initialize my seasonality to be, this is the multiplicative function. So I'm going to take the actual value divided by the mean level for the year. And then I'm going to do it for the first month here. And then months 2 to 11 is going to happen in this loop. Okay. And in months 2 to 11, I'm going to update the level and trend using the equations right here. But the seasonality, I can't update the seasonality using the gamma equation because I don't have a second observation of the same month. So continue to do the same thing for seasonality, which is take the actual y value divided by the mean level and say the difference from the mean level is due to seasonality. And then I can also build an initial forecast for the months 2 months 2 to 11. Remember, everything in Python is 0 indexed. So 0 is like row 1 in Excel, and row 11 is like the 12th month. Whereas in Excel, you can see that the month 12, which is row 13, is month 12. In Python, this is row 0, and this is row 11, which has the 12 months data. Okay. So when you do range 1 to MP, it'll give you values which are 1, 2, 3, all the way up to 1 below MP. It'll never give you the MP value. It does not include MP, the upper limit. It includes the lower limit, but does not include the upper limit, the range function. So I initialize my values, then I create my forecast and update my state, seasonality, level, trend for the next however many rows I have in the data frame. And then when I'm done with that, then I'm going to build a forecast for the next 12 months, for which I have to add new rows to my data frame. And then in the new rows, I'm going to build this forecast, which is the most recent value of trend, times 1, then times 2, then times 3, whichever month I'm going ahead, how much time I'm going ahead, times the last value of trend, and then times the seasonality. Add these two things and then times the whole thing, the seasonality. In the additive version, obviously, you're going to add the seasonality. You don't multiply by the seasonality. And instead of dividing by the mean level, you subtract the mean level for seasonality initialization. And in the main loop, when you update seasonality, the gamma equation, you're going to subtract right here instead of dividing for the multiplicative. So the formula is exactly like Excel. You have the gamma, alpha, the beta. You have df.log to get the value at a particular location, which is this row and this column. So df.log, then the row number, comma, the column name, lets you access that row and that column. And this works because I've reset the index to be based on row numbers. Okay. And let's run this and see what we get back. Okay. So before we can call this function expects that the date time variable must be set as the column index. Okay, so we're going to do that, and then we are going to call this function and see how our forecast looks like. Okay, so we'll say our column called month. Okay, let's just rename it. So our columns are called months, and then this hash passengers. We can say data.columns equals and give it a new column name. So we can call it year month, and then we can call it passengers or whatever else you want to call it. And this would rename our columns to how we want. So let's see, rename them. Now we can take the newly named year month column, right, and we can convert it by calling toDateTime function, toDateTime, and we can give it this column. Okay, and then we're going to say the format in this column, because it's not a standard date format, is year, 4-digit year with a dash and then a 2-digit month. Okay, because there's no day here, so it's like a little bit odd format, just year and month. There's no day. So pandas will be looking for a day as well. So tell them, okay, just this year and month. Don't look for a day. And then let's look at what happens, right? So now you can see it added the first of the month, because it's coming to a date time value, but we know it's monthly data because we don't have any days between the first of the month and then the next month. Okay. Now we're going to set this year month column to be the index. So we say set index. So the index is going to be the year month column, and we call it in place equals true to tell it not make a new copy of the data, just modify this data. And now you'll notice here's my index and here's my data. And now I'm ready to pass this data to the functions I wrote above, hold, winters, additive, and multiplicative. So let's start doing that. Okay, so I will call my forecasted data frame I'm going to call my Holt Winters additive function with the data. And then I can look at, the first 10 rows to see the output on what it gives me. So you can notice for the first 12 months, here's my level estimate, 118.6. If you go to your Excel, it's a little bit different. Trend is similar, seasonality is a little bit different. Okay, but it's close. So we'll look at our forecast and see if we get exactly the same values or not. Okay. And I think the difference is partly caused so we're very close, 127, 126.8. And if you look at our forecasts, well, we'll look at our forecast as well. Anyway, so it's very similar to what we got for Excel. And I believe the difference could have to do with the level of precision the different libraries keep. Okay, let's look at the last 2 years of values, so 24 values at the tail. And here you can see these are the 12 new rows added by our forecasting in future next year, and this is our forecast. So let's come back to Excel. We've got 449 and 432. 449, 432, same values. And then the last one is 479, 479.41. So we get the exact same forecast as Excel. So our code seems to be working, right? And now what we can do is we can, well, that's what you have to do. You have to write this code. You have to write this code. And then what you're going to do is you're going to submit the screenshot of all the plots you make, which you can only make if you write this code. Okay. Now we have to plot this forecast column versus the actual values column. But remember, we cannot plot the last 12 rows because there's no actual value. This is into the future. And we're not going to plot the first 12 rows because that's just initialization where our forecast is not very well off, but that's not too big a problem. And actually, we are going to plot this last row. We're going to see what our forecast looks like. Plotting is fine. For the error, to calculate the MAD and MAPE, we're not going to use these last 12 values because we don't have the true value. But for plotting, we can plot the whole thing. So the next is to, we're supposed to run the method in here. That's okay. We can just do it here. Again, we can just empty that out. Okay, the next cell tells us plot. So here we can use AI. We can say, okay, let's do a new one. Yeah, so we can say the plotting code. So what we can see here is make line plots of my passengers column in FCDF. Remember we called it FCDF, which has the forecasted data, which has the passengers column, and the forecast column on the same plot. Okay, so let's see, generates the code. Okay, figure size is nice, plots the passengers, plots the forecast, sets the labels. Excellent. Let's run the code. This is beautiful. So see, we got the blue, which is the original data, and orange is our forecast, and it's looking pretty nice. Okay, so we can delete this cell. So this screenshot you put into Word document to submit as part of this lab. Okay, next, so we did the additive seasonality. Next, we are going to run the multiplicative seasonality, which is a very similar code, just called that function. Okay, instead of edited, we call the multiplicative. Which is here. Okay, and let's call it FCDFM for multiplicative, so we don't rewrite the old one. Okay, and then let's see. Okay, here's our forecast with the multiplicative seasonality, and we can compare that with Excel. 457 to 477. Okay, and we got 457 to 477, exact same forecast. So it seems to be working well. Now we'll generate a new code block and give it a prompt. Plot the columns passengers and forecast from my data frame called FCDFM. Okay. Plotting, AI is really good at generating plotting code, so I just use AI to generate the code. And here is our multiplicative seasonality, and this one should be additive. So you can say actual forecast is passengers with additive seasonality. Okay, and then this one is with multiplication. Again, very nice fit, nicely tracking the signal. So our code is working, and we can delete this empty cell. This screenshot would go again in your submission for this lab. Now we want to compute MAD and MAPE to compute what happens in terms of error to our two forecasts, and does our MAPE and MAD kind of look like what we found in Excel, about 4% MAPE for both of them. Okay, so to do that, I've already given you a function which computes the KPIs of MAD and MAPE and returns them. And we can just call this function. This function is expecting the output of the Holt-Winters code, so it's ignoring however many values you tell to ignore at the end. The default is 0, but you can pass in 12 to ignore the last 12 rows, because remember, you can't calculate MAD and MAPE for the last 12 rows because there's no original data in the future, right? And then you can also tell it also ignores the first 12 values if you pass MP equals 12 to it. Okay, so we call this function, we say MAD comma MAPE, because remember it's returning two values. Remember, in bracket returning MAD and MAPE, two values. So we have two values be assigned to this result. Okay, Holt-Winters KPI. We want to pass it our FCDF for additive. Okay, that's the data frame. Our values are in a column called passengers, our data values. Okay, and our forecast column is actually just called forecast. Okay, and our MP is 12, that's default. We want to call it ignore the last 12 values. Okay, and then we'll print what just print out with format string this thing. The curly brackets means get the value of this variable and plug it in here. So we print out the MAD and MAPE. Oh, I have to run this cell to define the function. Then I run this cell. And you can see 4% MAPE just like we got in Excel. Okay. 4.11, 4.11 in Python. Now we call the same thing on the other data set with the same parameters, except we call FCDFM because that was the multiplicative one, and then we print out the MAD and MAPE. So you have to adjust this code, print these out, 3.95, 3.95 in Excel, and then you take a screenshot of this output, put it in your Word document. Okay. So now you have done Holt-Winters forecasting in Python, but the beauty is this code is going to work with quarterly data, monthly data. You can have like 100 products. You can call this function in a loop to forecast for 100 products and save all the forecasts into a database. You can do whatever you want with this easily. You can automate this, whereas you couldn't do that in Excel. You only write this code once. You can use it again and again in future, whereas in Excel you have to recreate the Excel file or at least modify it. Okay, so that's a big chunk of the lab done. Now we're going to do ARIMA models in Python. Again, if you don't know what ARIMA, SARIMA models are, actually we're going to use SARIMA models because we have seasonality in our data, which is obvious. We have monthly seasonality. You again have to go watch those lectures for the theory part This is a capstone course, so I'm not going to repeat all the theory from previous supply chain classes. So for that, we use the stats model package in Python. From the stats tools, we download this, import this statistical test, which tells us whether our data is stationarity or not. We import these functions to plot autocorrelations, and we import the sArima X function to do seasonal ARIMA modeling in Python. So let's see how to run the test. Remember, our data is in a data frame called data. So we're going to do all of this is in this data frame, where the passengers column has the passengers and the index is set to year month, which is the year and the month, and the day is just one as a placeholder. We don't know which, like, it's the sales for the whole month and not for this particular day. Okay, so how do we run this AD Fuller test on this data? It's actually pretty straightforward. We just call the AD Fuller function, okay, and pass it the column of our data values, okay, and that'll run the test. But we want to save the results. I mean, if you could run it like this, okay, and that'll give you all these values, but we want to print them out more nicely. So we're going to save the results in any variable, save it in X or whatever, ADF test. And then I'm going to print out the results, okay. So first I'm going to print out the ADF test statistic, okay, and that is going to be saved in ADF test, which is like a list of values, and the first element in the list, the 0th element, is the test statistic. And then I can print out the p-value, the ADF p-value, okay, and that is again stored in the output of the test, which is a list, and I take the second value, which is indexed at 1, okay, and let's see how that goes. So here, the test statistic is 0.8, p-value is very high. P-value less than 0.05 means there's no stationarity, which means you don't have a trend usually. But here we do have, it is non-stationary, so we're going to have to, make sure that our ARIMA models the trend. Now, we can plot the autocorrelations. Again, this is the data, and we can pass it to plot PSEF as well. And I'm going to say, show me maybe 3 years of lags, 36 months, right? We have 36 time periods, is 3 years of data. So if you can choose how many lags, at least 2 years you should always check. And then the PLT does show will just make it show the plot. So here's the autocorrelation function. You can notice it swings up and down. Every 12 months, there's a little bit of a small peak. That's proof of seasonality. And our partial autocorrelation function also has this huge negative correlation at 12, which is showing you the monthly seasonality. And then it has two partial autocorrelations at lag 1 and lag 2, which are significant. Outside the blue area, you have significant autocorrelation. Okay. And so these will help you choose the values of the parameters for the ARIMA modeling. Okay. Now we are going to do the actual ARIMA modeling, which is really easy because we just have to call this one function. And the way you do it is you first say, okay, my model equals, and you pass it that your data. Okay. Passengers. That's the column you want to do the forecasting on. Then you give it the PDQ parameters, which is a reminder. So I need maybe order 2 AR model. I need 1 to differentiate because it's not stationary. If it was a stationary time series, you'll just pass 0 here. But you will pass 1 because remember our test failed. We do have non-stationary time series. So most non-stationary time series can be made stationary by doing differentiation once or twice. So this is either going to be 1 or 2 or 0 if you have stationary data. So 1 is usually works well with non-stationary data, but if it doesn't work well, you can try 2. Maybe do 1 here. And then we want to pass in the seasonality parameters. So we can do seasonal order, And we can do, okay, maybe there's a trend in seasonality, maybe no. And then the lag is 12, so 12 months of seasonality repeats over 12 months. Okay, and this would set up the model. Then you can do model fit equals model.fit. Running model.fit will actually run the calculations, and then you'll get the fitted stuff. Then you can get your forecast by doing model fit.forecast. And we wanna forecast 12 months into the future. Okay, and then you can get your prediction, which is not going to be this. That's AI generated. Nope, I want it to be, just do it for the data that I have. So what's the difference in prediction and forecast? Forecast is in the future, for which we do not have true values. And prediction is, remember in Excel, I showed you this white part after the initialization, or with the initialization, this is this part where you have the true value and your forecasted value. You can calculate the error terms. So if you don't call predict, it's not going to generate this forecast column for these values. It's only going to generate the forecast column for the future, because forecast generates the forecast for the future, predict generates the forecast for the existing time periods. And we can start at 12 months to not factor in the first 12 months. Okay, and then we can print the forecast to see what our forecast is. So it's going to give you some warnings and stuff, but you can just ignore them. That's our forecast for the next 12 months. Now you want to plot that. Okay, so we add a coding block and use AI. So everything is stored in these models, right? So we have data passengers here, and then we have forecast and prediction. So make a line plot of data passengers and then plot forecast and prediction on the same plot in different colors. Okay, so we plot data passengers, forecast, prediction. Okay, let's see this. Here we go. So blue is the actual passengers. Notice we skipped the first 12 months. So it's not showing us the first 12 months for the green, which is the prediction. Prediction is for the time period for which we have data, so we can compare. And then the red is the forecast for the next 12 months. Pretty nice pattern fitting by the ARIMA model. Obviously, you can change things around. Okay, this looks pretty close fit. You can say, okay, what happens if I do just 1 here? If my P parameter is 1, how does that change things? So you run your code, and then you can run this code and see how that changes. Not much change. You could go for a simpler model with 1. Now, I already gave you a function to compute MAD and MAPE for ARIMA, which ignores the first 12 months. And then uses data and prediction. So we can just compute and print those values out. Okay, and we're going to pass in the data passengers and our prediction, and skip the first 12 values, and then we just print the MAD and MAPE. And this is using seasonal ARIMA, so S ARIMA. Oh, I need to close the brackets, parentheses. Oh, I have to run this cell to define the function, then I can run this code. And look at our MAPE is actually less than we got with Holt Winters, it's 3%. Remember, Holt Winters had about 4% MAPE, so we did a little bit better than Holt Winters with seasonal ARIMA. So we already did this plotting. So this plot will go into your Word document. This output will go into your Word document. Screenshot. Put this into your Word document for your submission. So this is great. You already are very far along. You can do Holt-Winter forecasting in Python, seasonal ARIMA forecasting in Python. You're already ahead of a lot of students in globally, because a lot of them are not taught how to do this stuff. So you already did the plotting. You can ignore that. Okay. Now, remember in this S-ARIMA model, we to specify the parameters, kind of guess them looking at the PSEF and ECF plot. And let's say you don't want to guess, you want to automate this. So different products, different categories, they want different values of these parameters to do a good job. So how do we automate this forecasting? Again, these lectures talk about, the last one talks about automated forecasting with things like AutoArima, talks about the theory. So you can look at those lectures, but how to do it, let's use AutoArima. So we have to install this package called PMD Arima, and that has a function called AutoArima that we don't have to specify the parameters for Arima. It tries different parameters and finds the optimal ones. So we run this install command to install this package because the Google Colab Notebook doesn't come with this by default, so that's installed. Then we import it, okay, and then we're going to run it. So we can say use the PMD Arima package imported as PM to run AutoArima on data passengers. Let's see if he does a good job. Otherwise, I'll tell you what to do. It's very simple. Just call AutoArima function with seasonal parameter set to true, and m equals 12. Very good. This is the command pm.autoarima, because we import as pm, data passenger seasonal true, m equals 12. Very good. And then you can do, and I'm going to call it model auto because model was what I called my S-ARIMA model up here, so I don't want to overwrite that. See, this is my model. So if I reuse that variable, it'll overwrite it. I don't want to write it. So I'm going to call it model auto. Okay. And then I can just do model auto.summary to see how it went. So it's going to give you a bunch of warnings because it's based on the sklearn library, and that has some, you know, they're changing some function names. It's giving you a warning that in future, but you know, the package will update by that time. So don't worry about those warnings. Okay, so it applied 211 S-ARIMA, and for seasonality it did 010. And then did a lag of 12. So very similar to the parameters we used. Okay. And now we can actually run the predictions. So we can say the forecasted value from this AutoArima, we can just do model auto, dot predict. Now this package calls it predict instead of forecast. And we say the periods 12. So predict the next 12 periods. And then my prediction over the years for which I have real data is going to be model auto predict in sample. Okay. So I can run those predictions. And then I'm going to plot everything. So I'm going to call AI. Okay, make a line plot of data passengers. And on the same line plot, do plots of forecast auto and prediction auto in different colors. Okay. So very nice. Plot this, plot this, plot this. Ta-da, looks like good code. There we go. So blue is the actual data. Green is our AutoArima forecast. Notice it doesn't do very well for the first 12 months because it's initializing. See, that's why I started 0, but you can ignore that. And then red is the next 12 months into the future. So very similar to what we got from our ARIMA model. See, very similar. So take a screenshot of this, put it into your Word document to submit for this lab. Now we can calculate MAPE. We can use the same function for that computes ARIMA KPIs. We pass it the data passengers, and we pass it our prediction auto, which is the prediction over the same time period. We want to ignore the first 12 values, MP equals 12, and let's see the AutoArima MAPE. And we got 3.45, a little bit worse than our ARIMA, right? We got 3.07 here. So, you know, it tried different parameters, maybe didn't try a large enough range of parameters, but it's very close to what we got with manual fine-tuning. So AutoArima is pretty good. It'll get you really close to what you can get with manual fine-tuning, and you don't have to worry about guessing parameters. You can just call so easy. Just call AutoArima on all your time series in a loop. If you have 100 products to forecast, run a loop 100 times, you get done, and it works pretty well. Okay, so take a screenshot of this plot, take a screenshot of this, and we're almost done with the lab. The last thing I'm going to show you is how to use the Facebook Profit algorithm package, which is a very good forecasting package for daily data, if you have daily sales. Why? Because it has a lot of stuff for holidays built in. It has built-in adjustment for different month lengths. Let's say a month is 31 days versus a February 28 days, things like that. So you can do a lot of advanced stuff like that. And Python already has packages for different countries which identify the holidays. You can just import the package for US holidays and give it to Profit, and it will know what are the national holidays in your data set. If you have global data for different countries, you can just import the holiday data sets for different countries into Python and pass it to the Profit package, and it will incorporate the holidays, because some products they sell more in holidays, some sell less, and it can do that sort of adjustment by looking at the holidays like that. So we install the package, we import it. Now, if you look at our data set looks like this. Now, Profit does not want this date column to be an index. So what we're going to do is we're going to say reset index in place equals true. Okay, and then let's do data.head. So Profit wants it like this. The index should be row number 012, and then your date column and this column should be here. Then it also wants the columns to have a special name. It wants the date column to be called DS, like date stamp, and your column that you want to forecast to be called Y. So we rename our columns, okay, to pass it on to Profit. Actually, I should probably make a copy and call df equals data.copy, and then do all this with df. Okay, so to not mess up my original data. Oh, okay, so I want to read in my data again, because my data got an extra column because I ran the code twice. So let me just run this code to get my data in this default way, and now I can reach at the end, make a copy, and do all of this stuff, and here we are. So DS column has the date timestamp, Y has this. We're going to do one more thing. The Profit, because it's designed to work with daily data, it's going to think this is daily data, especially because we have a day here as well. So we want to tell it that the frequency of our data is monthly, and not daily. Okay, so we're going to have to do one more thing, which we did not do up here, but we can do it now. That's not a problem because we didn't need to do it before, which is to set the frequency, okay, to be monthly. So the way we do that is we call the index property of our data frame. Okay, so what we're going to do here is this. We're going to say df.index.frequency equals month start. So each date represents like the start of the month, or you can just do month. That's fine, just month. It's just the monthly frequency. And then this will tell Profit that this is not daily data, this is actually monthly data. Now we actually run Profit to do our code. So let's say our forecasted by Profit FCP, okay. Profit has, first we have to create a model. So model P, Profit model just equals Profit. We create the model, okay. Then we're going to call it to fit. So our model P dot fit on our data frame, which is df, which you just set up here to work with Profit. That's going to fit everything. And then we can say our Profit forecast, P forecast, is equal to m model P dot make future data frame. okay, for the next 12 months. Actually, this is just the future data frame. And then we call predict to actually get the prediction for the future. So we run the model, we make a data frame to have 12 more time periods, and then we call predict to do the prediction for the next 12 and the existing time and the future 12 months. Okay, now we're going to call AI to make the plot for us. So plot, make a line plot. Oh no, we can actually just call Prophet to plot, because Prophet has a nice plotting function where you can just call, you don't have to work with the matplotlib. So we can say our figure equals model p dot plot. We give it the prediction p variable from here, which has the prediction. And then we can just say figure dot title equals Prophet forecast. Okay, and then we can do figure dot show. Okay. Sorry, we used PLT. So figure is going to use the PLT package to generate the figure. Okay, so notice this, it's a nice looking plot because Prophet uses a little bit different library to create the plot. The black dots are original data. The blue line is our prediction, and notice our prediction goes 1 year into the future because our data stops right here. This is December 1960, and then from 1961 we make our prediction as well. So pretty nice fit of the data. Let's check the error. Now because the data Prophet returns, let me show you. Let me show you what prediction P looks like. So because the prediction P dot head, let me show you 10 rows. It has a lot of columns. So it has a trend, it gives you all the components broken up, the trend component, it gives you seasonality terms, multiplicative, additive, it gives you the upper lower bounds. Y hat at the very end is the actual prediction. So it gives you a whole bunch of information. So to calculate the KPI, we have to make sure that we do it properly. We access the right columns and stuff. So I made a new column which does things a little bit differently to compute the MAD and MAPE, just to address the differences in the data structure here. So you can just use this function to call MAD and MAPE for Prophet, and we're going to pass it in our original data, okay, which is data passengers, and we are going to pass it in our prediction P Y hat. Okay. Now we do want to do we want to do one more thing. So let's do that actually. The other problem we have is our prediction. This data set, if you look at the tail, let's look at the last like 20 values. You'll see, okay, it's going to 1961. So the last 12 values, there's no original value for that. So we can't pass it in the last 12 values. So what I'm going to do is this. Y hat equals prediction Y hat dot ilog, and just take all the values which go up to my data and ignore the values which the 1961 values. So then data will give you the number of rows in the original data up to December 1960, and I ignore the additional last 12 rows that it added, and then I just pass it in this Y hat variable. Okay, and we can pass it in MP12 to ignore the first 12 values because you're just initializing your algorithm at that point. Okay, and look at our MAPE. It's a little bit worse than AutoArima and Arima. They give us 3.53, and this is 6%. This Prophet does not perform the best usually in terms of error rate. It's close. It's in the ballpark, but doesn't do the best. But its strength lies in its flexibility. It can deal with different lengths of months. It can deal with holidays. It can do with 2 levels of seasonality. Let's say you have day of the week seasonality between Sunday, Monday, Tuesday, Wednesday, and you also have monthly seasonality, and you also have quarterly seasonality. It can deal with multiple seasonalities at the same time. So it's a very flexible and powerful package. You can just Google, Facebook's Prophet forecasting package, go to its website and look at its documentation. But it's very easy to run. You just call, model.fit, and then you can make future data frame and make and predict function, do all the prediction for you, and then you can do the plotting. You can calculate, KPIs, MAD and MAPE, and that's how you can use this very flexible package that many companies use this for their forecasting. So see, Python makes it easy to bring in so much advanced analytics. You can bring in Arima, seasonal Arima, bring in Facebook's Prophet package. With a few commands, you can do very advanced forecasting work. So again, you're going to submit me a screenshot of this, put it into your Word document, take a screenshot of this, put it in a Word document, and you're done with the lab. Go ahead and submit the lab. If you have any problems running this code, I'm showing you all the code in the video, so you can just kind of use this code. If you have any problem doing this lab, you can reach out to me. And then the theory is explained here. So hopefully this will get you up to speed to a basic competent level of being a forecaster with time series data. And this is something not a lot of students can do, but it's a very practical skill. So I'm happy to teach you this. And so you can tell your employers or in your interviews that you've actually been taught forecasting in Python, and you can improve your skills. If you do want to become like a professional time series analyst / forecaster, this is a really good book you can do in Python called Practical Time Series Analysis by Eileen Nielsen. Really good book. If you go through the whole book and you master it, you will be very valuable to your company. So money well invested. It doesn't cover the Facebook's Prophet algorithm, but it does cover Arima. As Arima, it does cover new machine learning models as well. You have to shape the data set differently to run machine learning models like XGBoost. This lab would have become too long for me to include XGBoost or the machine learning models, so I didn't do that. But you can learn that if you go to that book. As you get more comfortable with Python, you'll realize you can do a lot of cool stuff.